Okay, we're going to go back to Chapter 2 today. So, Chapter 2 and 3 kind of go together. That's why we waited a little bit to do these instead of going in order. This is really kind of the bulk of Chemistry 1. So, I know we've named and we've done quite a few things that are very important, but these calculations you'll build on through the rest of the semester, and if you take Chem 112, you'll build on them then as well. So these are, especially Chapter 2 and really 3, but it's imperative that you learn these calculations today. And it's not that they're hard. It's really the same thing as you've been doing with converting from inches to feet or milliliters to liters or whatever. We've been using conversion factors. And it's the same thing, except for now you have new conversion factors. You have new relationships that you can use to do calculations. So it's really very similar. You want your units to cancel. You want to write out what you know first and go from there. So and kind of make a plan and then move on from there. So, but the first thing we're going to talk about, we may or may not get through all of this today, but what's a formula, a chemical formula? So this will be pretty simple. We kind of done this anyways, but then we're going to look at the mole. Has anybody ever heard of the mole besides the animal? Yeah, so it's just a quantity we use in chemistry. So we're going to talk about what it is and how we relate it to our other quantities and how we can convert from, moles to other units. Okay, then we're going to look at formula weight, molecular weight, and moles, okay, or really it's molar mass. I should put that there. Okay, and that's really just adding up the weight of or the mass of a compound, so not too difficult there. Then we'll look at percent composition, so we're just looking at some percentages, and maybe the hardest part will be just deriving some formulas. So I don't know if we'll get quite there today. We might, but and then we'll look at 5 and 6 go together, so we'll do those together, and then we'll look at some purity issues and percentages. Okay. So a chemical formula is just the substance or the composition of whatever substance that we're looking at. So, and it tells you the ratio of your atoms. Okay, so if you have just one single atom, we just call this a monatomic element. So if I just say helium, magnesium, carbon, and there's just one, so you think of one as mono there. Okay, here's diatomic. We've already discussed these. It's when the same atom's bonded to itself. So oxygen, chlorine, fluorine, F2, Cl2. We don't do a lot with these. So there's ozone. That's a pretty common one where you have more than 3 of the same atom bonded, but there's not a whole lot of these. So you can have P4, S8, okay, but that's just, by itself, that single atom, but there's multiple of them. So they're a little bit more complex elements. Compounds is what we're going to be focusing on mainly. Okay, so either, these two up here, but mainly a lot of compounds. So here we've got, water, C12, H22, O11. Okay, so if we look at a compound, so this is pretty straightforward, but a compound means that you have 2 or more atoms bonded together in a specific ratio, right? Okay, and they're in that ratio for a reason. Okay, and we know now we've drawn Lewis structures and we've looked at electron diagrams. We know that it's not a coincidence that things bond, that water has 2 hydrogens and 1 oxygen. Okay, it has 2 hydrogens bonded to it because it needs 2 bonds and 2 more electrons for that oxygen atom to have 8 to fill an octet. Okay, so there's not a coincidence that the formulas and the structures look the way that they do. Okay, so in HCl, it's understood. You don't have to put a 1 as a subscript there. Okay, it's understood there's just 1 hydrogen and 1 chlorine atom. Okay, if we look at H2O, we've got 2 hydrogen atoms and 1 oxygen. Okay, and so this is pretty simple. 1 nitrogen, 3 hydrogens. Okay, this is propane, C3H8. We've got 3 carbons, 8 hydrogens. Okay. On Blackboard, there is a handout for Chapter 2 and 3, And it's just actually kind of a nice outline for you, okay, so that you can, read through it and then, build upon those points as we learn more in class or you're reading through the textbook. Okay, but there's also a list of some compounds that every chemist should know. Okay, I've cut you a break on some of them. You don't have to know all of them, okay, but the ones that are underlined are the ones that you will have to know. So one of them is water. You have to know that water is H2O, okay? Another one, methane, it's CH4. Okay, so you have to be able to know some of those compounds. Okay, and so on the exam or any of the homework, I might say, what's the molecular weight, which you don't really know what that is yet, of methane. So I may not give you that it's CH4. Okay, you have to know that by looking at and studying those compounds. So I'd go ahead and start doing those, make flashcards, that kind of thing. Some of them are real easy. Some of them are a little bit harder. One of them is benzene. It's C6H6. And that's one that, some of you may not know that one. Okay, I left this in here. I used to talk about polyatomic ions here, but we've already discussed this. We've already talked about how to name with them, but this will be good review. So that's why I kept it in here. So you can review that, be sure that you understand how to name using polyatomic ions, which is, like I said, that's what we did on Monday. Okay, and so here's some more that you can practice. Okay, so the number on the periodic table that is underneath the element symbol, okay, that's the atomic weight, right? Okay, it's not the mass number. Okay, remember, a mass number is the whole number. It's the atomic weight of that element. Okay, so that means that it's the weighted average of all the isotopes of whichever element you're looking at. So here would be magnesium. Okay, so the number here, it has a decimal. It's not just a whole number like a mass number. Okay, and it has the units. So there's actually lots of units, but the one that you see commonly in the beginning of chemistry anyway is just AMU. So we'd say that we have 24.305 AMU. Okay, that's the unit. That just means that's the atomic mass unit. Okay. All right, but what we want to know, so we've established that. That's the atomic weight. Great and wonderful. It's also called the atomic mass. Okay, those are used interchangeable. Okay, but what does that mean to us? Okay, so how can we use that number? What is it related to? How did they come up with this? We know we took the weighted average of the isotopes and placed it here, but how can we compare that number, and what does that mean when we compare it to another element? Okay. So this is where the mole comes in. Okay. When we are dealing in chemistry with thousands to millions of molecules or atoms at a time, okay, we need to be able to deal with and look at a mass that we can actually measure out, that we can, go to the balance, measure out, and we can describe it being a larger number. So if you think about, a dozen, okay, that means 12 things. Everybody knows that, right? So you say if a dozen, that's 12, no matter what. Okay, well, a mole is basically the same thing. It's just a number of things. Okay, and in chemistry, those things are particles, atoms, or molecules. Okay, so whenever you hear those terms, you want to think of the mole. Okay, and a mole is always equal to 6.022 times 10 to the 23rd things, particles, atoms, molecules. Okay, so this is Avogadro's number. A lot of times I will write just NA, that's just the symbol. Instead of me writing out 6.022 times 10 to the 23rd, you'll see me write this out here. Okay, so this is a number you have to know. Okay, so it's one that you just got to memorize. But instead of us trying to describe matter or atoms or particles in these huge quantities in thousands and billions, we relate it back to a mole. And just like we say, that's a dozen instead of saying 12, which isn't really a whole lot, but that's the same idea. So a mole is always equal to that many things. Doesn't matter if we're talking about magnesium, titanium, carbon, any of those. Okay, any element that we're discussing, or particle or molecule, 1 mole is always equal to 6.022 times 10 to the 23rd. Okay, so we've established what a mole is, and the question was, how do we relate this to our periodic table? Okay, that's our handy-dandy friend, right, that we look at for numerous things. Okay, but if we look at it and we see those numbers under the element, okay, and it's the atomic mass unit, okay, but how are we going to relate this to a mole, or what does that mean? Okay, and the answer is that every number, so get out your periodic tables if you don't have them out already, okay, every number on there for the atomic weight of an element is based upon 1 mole. So every time that you look at your periodic table and you see and you use, we're going to use those numbers in calculations, whatever number is under the element name is always based on 1 mole, which means how many things? 6.022 times 10 to the 23rd. That's a really large number, though, isn't it? Okay? Yeah. So we use that as our kind of, standard one to base everything else on. Okay? Because it's a large number. We're dealing with large quantities and large numbers of atoms. Okay? All right. So the mass of 1 mole of an atom of a pure element in grams is numerically equal to the atomic weight of that element on the periodic table. Okay, so that's pretty much what we've just said. But the main thing here that you want to see is if we have 1 mole of titanium, so that's just an example. So everybody find titanium on your periodic table. Okay. It should be about 47.88 and maybe a little bit different depending on the periodic table. Okay, that means that we have 47.88 AMU, atomic mass unit, in 1 mole. Why? Because every number on there is based on 1 mole. That's our just common relationship between all the elements on the periodic table. Okay, it also means, so this is where this is super important here. If you have 47.88 AMU, you also have 47.88 grams per mole, okay, because you are basing everything on 1 mole, right? That number is based on 1 mole. Okay, grams is very useful to us, right? We use it all the time. We take the mass of something and you report it in grams, okay? And it's also equal to, our relationship in the beginning here was 1 mole is equal to 6.022 times 10 to the 23rd. Okay? So the atomic weights on the periodic table are always based on 1 mole. So I already said that a few times. Okay? But when you are, a lot of times students get this, but then they start doing the calculation and they start throwing in numbers that aren't needed quite yet. Okay? And the reason for that, or why I try to prevent that, is if you get a number off the periodic table, you get an atomic mass off the periodic table, it is based on 1 mole. Okay, so there can't be any other number with that besides whatever the AMU is per mole. Okay, it can never be anything other than 1 because that's what our periodic table is based upon. Okay, so if we look at magnesium, 24.305, some of yours may say 3.1 or whatever. Okay. We have 24.305 what? What does that mean to you now? Okay, not moles. Okay, exactly, that's a good one. So 24.305 grams per mole. Okay, 1 mole is equal to this, right? All right. We have 24.305 AMU too, right? I agree with that. Okay, we have grams per mole, and we also have, if we have 1 mole, we have how many things? Or how many atoms in this situation? 6.022 times 10 to the 23rd. Okay, I'm not too picky. If you want to just memorize 6.02, that's fine with me too. But usually I put it up here as 6.022. Okay, so we're going to use the mole to measure and help us describe quantitative relationships of particles and atoms and molecules. Okay, so we're going to start converting. Hey, can everybody in here convert from inches to feet? Everybody? You all did it on your exam? Yeah. This is the same thing. We just have a new relationship. So if we were to add a conversion factor, does everybody remember your conversion factor sheet I gave you on the exam? Okay. What could we add to that now? 1 mole is equal to 6.022 times 10 to the 23rd atoms, particles, or molecules, or things, if you want to even think of it that way. Okay, anything else we could add to that? What about our grams per mole? Okay, so we could add that our atomic mass, which wouldn't really, I guess it would be dependent on whatever the atom is, but you know now that whatever number is under that element, that is in grams per 1 mole, right? Okay, so that's why I added here that these problems are simply conversions. For some reason, when we throw in moles or an Avogadro's number, students just that just throws them for a loop because they're used to inches, feet, milliliters, liters, gallons, quarts, whatever. But it's the same idea. So we're going to go through the same strategy that we've been using. That's why it was so important that you learn to convert in Chapter 1, and because now you're going to build on that. Okay. So the first thing we always do is write out what we're given. Okay. Not only the number that we're given, you write out the unit as well. Okay. And then from there, we devise a plan, and then we cancel our units so that we're left with whatever unit we want to find. Okay. These first couple of problems they're one step. Okay. But we're going to build on these. So you have to get this one step, or later on, it's just going to become, a little bit hectic for you. Okay. The first thing we're going to look at is being able to, I already have the answer up here, but I'm going to go through it, to convert from moles to grams. Okay? So if I was to tell you, Abdullah, go measure out 3.451 moles, what would I tell you that in the lab? What would you do? Is there anything in our lab that measures moles? Okay, so what do you think you could do to solve this problem? Anybody? Okay, but what are you doing? You're converting, right? You can convert moles to grams, and then what could you go do? But what could you do in the lab? If you converted from moles to grams, and then I said go measure out 83.89 grams, what could you do in the lab? You can go, right? You can go to the balance. It might be a little heavy for it, but you could go over there and you could measure out 83.89 grams, okay? So the idea here is if you're given moles, and that's our new kind of relationship here. Remember, it's just a quantity that describes an enormous amount of molecules or atoms or particles. Okay, we can convert to grams, and then that's useful to us, right, in the lab. Okay, so this is the reason that it's useful. So the first thing that we always do is write out what we know, all right? And for this, you're also, watch this be dead. It's not been on the charger. Let's see. Where's that thing would go away? Okay. We write out what we know. 3.451 moles. Okay, and here's something new. It's going to seem simple at first, but you need to get into a habit of writing the unit and the compound, or here it's just an atom. Okay, so we have 3.45 moles of what? Magnesium, exactly. Okay, we do our little multiplication sign there. We write out our next fraction, Okay? If our units on top is moles of magnesium, what has to be our units in the denominator here? Moles of magnesium. Okay, in chapter 3, we start converting from moles of one compound to moles of a totally different compound. Okay, so that's why you want to keep up with what compound it is. Okay? Okay. So if the two relationships we talked about are mole, Avogadro's number, and then being able to use our periodic table to get grams per mole. What do you think what relationship have we talked about that we could now plug in here to give us grams? Okay, we know we're looking for grams, right? So it's going to be up here, not canceled out, right? Okay. So what relationship do we have here? Okay. Okay. That was a good try. She said we could have 1 mole on the bottom. That's correct, because everything we've looked at has been based upon 1 mole, right? Okay, and you'll see why I emphasize this later, because as we build on this, students want to start putting more moles and things in there. Okay, but she said to put Avogadro's number on top. Okay, but if we put Avogadro's number on top, what are we finding? Okay, Avogadro's number was 6.022 times 10 to the 23rd particles, atoms, molecules. Okay, so that's a really good try, but we're looking for what? We're looking for grams, right? So those units don't quite match up. Okay, the mole does, but the Avogadro's number doesn't. Okay, so the 1 mole does. Okay, but if you look at your periodic table and you look for magnesium, in 1 mole, how many grams do you have? Exactly. So you use the atomic weight or the atomic mass of magnesium. Okay. So repeat that to me. What was it, 24.0 or 24.3? 305 or 30? Okay. All right. So it should give you, so now look, we can cancel moles magnesium, moles magnesium. We're left with grams magnesium on top, which that's what we need, right? That's what we're finding. Okay, and we should get about this number, so it may be a little bit different depending on what periodic table I used. Okay, and that's it. It's 1 step. So the overall picture here is to convert from moles to grams. We multiplied times the atomic mass from the periodic table. That looks like an O, but that's an A. To get to grams. Questions? Bless you. I am tired of this thing that keeps going up. Cannot get rid of it here. Okay, now we're going to look at this problem in reverse. Okay, so this problem says how many moles of magnesium atoms are present in 73.4 grams of magnesium. Okay, so we want to know that moles, that's that big number, right? That 6.022 times 10 to the 23rd. Okay, we want to know moles from grams. So we're going now in reverse. We're going from grams to moles. Okay. So what's the first thing we always do? Yep, write down what you're given. Okay, you have to know where to start. That's the easiest way to know where to start. Go ahead and draw our next fraction here. We know grams magnesium has to be in the denominator because it's going to cancel. Okay, and we know we have a direct relationship between grams and moles. That's why we know it's just a 1-step problem. Okay, we know that we're going to end up, we have to have what? Moles up here of magnesium, right? Okay. All right, so what's our relationship here between grams and moles? What are we going to plug in? Okay, we always have 1 mole. So if I go to my periodic table and I get a number off there, it's based on 1 mole. That's the common relationship of that periodic table to every element on there. Okay, so 1 mole of how many grams? Exactly. So all we did was divide by the atomic mass. Grams cancel. We're left with moles. I have the answer underneath here, but I don't remember what it was. Anybody have their calculators out? 3.02? So our final answer is not, it's not just 3.02. It's what Darby said. It's 3.02 moles magnesium. Okay, so we have a unit, and we also tell what atom or what compound that we're looking at. Okay, so you can't hardly see that, but these 2 problems seem simple, but we're going to build upon them. Okay, so you have to know how to do these. Okay, this is going to be the beginning of many problems from here on out. All right, let's look at this one here. I already gave you a hint, but this time, Cassidy, we're asked for atoms. Okay? So if that is in your problem, either you're given atoms, molecules, or particles, or you're asked for atoms, molecules, or particles, what number do you want to think of, Cassidy? Okay. Okay. It's what you were trying to do earlier. That's why I asked you. What number did you try to use earlier? Avogadro's number. Okay, here is where you will use Avogadro's number, because what are the units for Avogadro's number? Particles, atoms, molecules. Okay, what do you ask for? Atoms, right? Okay, so if you see that, you would automatically think Avogadro's number. Okay, so that's why I wrote it down here. Remember, 1 mole is equal to 6.022 times 10 to the 23rd. Atoms, molecules, or particles. Okay, so the first thing we do is we write out what we know, the 1.67 moles magnesium. Okay, I keep using magnesium just because we've already established what the atomic mass is, but you can of course do this with any of your elements. Okay, and we know once again that there's 1 mole, so our moles can cancel. Okay, 1 mole of magnesium, 1 mole of any atom. That's the cool relationship here. Is there's in 1 mole there's always 6.022 times 10 to the 23rd. Okay, so like I said, that could be titanium or water or anything, and it's still 6.022 times 10 to the 23rd. Okay, so these cancel. We're left with magnesium atoms on top. Because of this scientific notation, these cause calculator errors. So you want to be sure that when you're practicing these, and there's lots of practice that I've posted on Blackboard as well. I would do those worksheets along with the OWL. But be sure you get the same answer, because if your calculator's not doing right and you don't figure that out till your test, then that's not going to be good, even though I'll still give you partial credit. But we get 1.00 times 10 to the 24th magnesium atoms. All right. So we got to take a break for a second from this grams to moles, moles to grams, because we've just been looking at a single atom. Okay, so we use magnesium for all of those. We could have used titanium, carbon, whatever. Okay, but a lot of times, especially when we start looking at chemical reactions, we're dealing with compounds. Okay, so one of the most common, H2O or sucrose, or there's, thousands that we can use. Okay, so we have to be able to add up the atomic mass, all of the atomic masses for all the elements in a compound. It's really not difficult at all, but we have to show this. Okay, so there's some terminology, and this is on your outline that I have posted on Blackboard that'll help you. So we're going to go through what the terms are, and then we're going to show them. So you have that really usually makes more sense. Okay, so we use some of these terms interchangeably when we're talking about, basically, we're talking about the mass of a compound. Okay, so you've established that you can come up with the mass for a single element, but we need to come up with the mass for an entire compound, so whatever that might be. If you use the term formula weight, basically you're safe in respect of it's going to include covalent and ionic compounds. So I can say the formula weight of NaCl is, I don't remember right now, 50-something, okay, 59 I believe. Okay, and then if I could also say the formula weight of water is 18. Okay, and the reason both of those are correct, one was ionic, one was covalent, but formula weight is the correct terminology. Okay, if you say molecular weight, okay, this does not include ionic compounds, so that's just not correct. You're supposed to say formula weight for an ionic compound, and for a covalent compound, you can say molecular weight. Okay, so it means molecular means covalent. Okay, all right. So first off, real quick reminder: what's covalent mean? What's a covalent compound? Share electrons between nonmetals. Okay, so water, is it a covalent compound? Okay, what about methane, CH2? Covalent? Yeah? Okay, what about lithium bromide? Covalent? No, it's ionic because it has a metal, right? Metal and non-metal. Okay, the one that we're going to use the most is the molar mass, because this helps us in our calculations. And basically, you add up the formula. So we're about to show you how to do this. I'm just giving you the correct terms. You add up the formula, and because our periodic table is based on 1 mole, then we can say the molar mass of a compound is blank grams per mole. And you can see how that would be useful, right? We just did calculations with grams and moles. Okay, so this is going to be a useful term for us. Okay, so how do we do this? So if we're looking at the formula weight, so we can use that term for any compound. So you're safe when you use that term. Okay, we look at the periodic table. Imagine that. Okay, here we have propane, C3H8. Right? What's the difference in this and magnesium? Just a simple question. Magnesium is just a single atom, right? So that's why we were finding atoms. Now we have what? Compound, exactly. So now we have to add up the mass, or the formula weight. All right, so you look at your periodic table, and you see that in your formula, you have 3 carbons, right? So 3 times 12.01, that comes from your periodic table, right? The atomic mass gives us 36.03. Okay. What else are we going to have to add up? Hydrogen. Yep, we got 8 of those. So 8 times 1.01. That number, once again, came off your periodic table. And then we simply just add them together. So you're just adding them up. You're getting the sum, adding up the sum of all of the atoms in the compound, okay, times their formula weight. Okay, and here our units are AMU. That's just one of our units we could have. So we total it up, and we'd say the formula weight of propane is 44.11 AMU. Okay, easy enough? All right, what about, how do we name this? Never mind, it's up here. Calcium nitrate. Okay, so we have a polyatomic ion. Okay, 1Q for that is that we have those parentheses, right? Okay, we have a metal, and then it's in group 2. So we just simply name it. It's calcium, and then we look at our chart, and O3 is nitrate. Okay, so no Roman numerals that are needed. Okay. The next question is, how many calcium atoms do we have? 1. Okay. How many nitrogen do we have? 2. Everybody agree with that? 2. Okay, what about oxygen? 6. Okay, you multiply the number on the outside of the parenthesis times the subscript on the inside of the parenthesis, which sounds like most all of you just answered that and would do that. Okay, so that's the first thing you have to do in order to be able to add up the formula weight. Okay, so technically right here that should be formula weight. Okay, so we take 1 times 40.08. Where did that number come from? Periodic table. And then we take 2 times 14.01 because that is the atomic mass of nitrogen. And then we have 6 oxygens, and we have that's 16 is the AMU for oxygen. So we get those numbers, and then we add them up, and we get 164.10 AMU. Okay. If we wanted our units to be in molar mass, which is what I was trying to do here, and we would be grams per mole, right? That's what molar mass was. It's just to add it up, and then your units be grams per mole. Okay, this would be a good question, good test question. Okay, right now you probably haven't memorized unless you're just a really on the ball, all of your compounds that you should know. Okay, one of them is acetic acid. Okay, so does anybody know the formula for acetic acid? Okay, well you will by test time. Okay, so I'll give it to you. Okay, sometimes it confuses students how it's written. Okay. It's written this way instead of C2H3O2. Okay, that's not wrong. It's written this way because that's the way you draw the Lewis structure. Okay, so the Lewis structure of acetic acid is this. Oh, I don't know what's going on there. So it's written in this order. I get this question a lot. That's supposed to be an H. It wouldn't let me do it because that's how it's drawn. So it just helps students to be able to draw it, or really anybody. That's how you see it written instead of C2O2H4. Okay? Because you write it CH3 is bonded to a carbon, to double bonded to an oxygen, and then to the OH here. Okay. All right. So find the molar mass and report it in the correct units. Okay, so I'll give you a couple seconds or a minute to do that. Okay, so add up the molar mass of acetic acid. Anybody get 60.06 or close to that? Okay. You have 2 carbons, so 12.01 times 2 2 oxygens, so 2 times 16, and 4 hydrogens, 4 times 1.01. Okay, and like I said, periodic tables are a little bit different. If it's, off a decimal or so, then that's fine. Okay, my units are grams per mole because I told you to find the molar mass, right? Okay, and that's going to be really useful in our calculations. Okay, any questions on that? Everybody get 60.1 or 60.06? Okay. So now we're going to take what all we've learned and put it into another problem. Okay, we can convert grams to moles or moles to grams. Okay, we can also now come up with a molar mass, right? So C3H8 propane, you already did that on a previous slide, and I think it was like 44.11. Okay, so we already added that up, grams per mole. Okay, now we're going to look at this problem and look at what we're asked to find. Okay, and we of course always first start with what? Just writing out what we're given. Okay. Okay. Now I want you to think about our new conversion factors, our mole and our atomic mass, our grams per mole, our molar mass, and think about Avogadro's number. Okay. Think about all those relationships. Okay. Here in bold, we're asked to find molecules. So what do you automatically think about if you have to find molecules? Avogadro's number. It's got to be in here somewhere that you're in your problem, and it's going to be probably the last step, right? Because that's what you're finding. So you want it to be, not canceled out and last in the problem. All right. But what's our relationship? Avogadro's number is equal to what? 6.022 times 10 to the 23rd particles, molecules is equal to 1 what? Mole. All right. Well, we're in grams. So we can't directly relate 74.6 grams to Avogadro's number, can we? No, because 74.6 grams doesn't equal 6.022 times 10 to the 23rd. Okay? So we're going to have to first go from grams to moles, our one step that we did earlier. Okay? So we do this by adding up our molar mass. Okay? So in this denominator here, what number am I going to put? Exactly. You have to add up your molar mass. So we did that on a previous slide. Okay, so we have 3 carbons times 12.01, 8 hydrogens times 1.01. That equaled what? 44, wasn't it? 44.11, something like that. Okay. So now, the only difference in this and when we had magnesium is that we have a compound now. We don't just have a single, we can't put just 12 there because that's just one carbon atom. Okay, we have a compound, so we have to add it all up, get the molar mass, and now we have a larger number there. Okay, if we use the periodic table, it does not matter that this is a compound and that magnesium was a single atom. It does not matter. It is still based on 1 mole. Okay, always. If you go to that periodic table, it's 1 mole, always. Okay, so up here is 1. At this point in our calculations, we've never used anything but 1 mole, right? Okay, so it's always 1 to this point. Okay, next week, that'll change. Okay. All right. Now we have moles, but moles and molecules are not the same thing, right? Okay. We know a relationship between the two. Okay, so don't accidentally abbreviate molecules as moles, okay, because they're not the same. Okay. So if we add a second step, just like you would in a typical conversion, if you had 2 steps, you're going to have moles in the denominator, right? Because we have to cancel again. Okay. We said we're going to have to use Avogadro's number. Okay. So how are we going to plug this in? Are we going to plug it in as 6.022 times 10 to the 23rd over 1, or 1 over 6.022 times 10 to the 23rd? 1 at the bottom because it's always 1, right? So really 1 mole would be better. And then we plug in, I'm going to abbreviate it as Na, but that's 6.022 times 10 to the 23rd molecules of propane. So when we do the math, we end up with 1.02 times 10 to the 23rd molecules propane. Okay, so we took our one-step problems and put them together. Okay, the main thing here is you're given grams, and there's not a direct relationship for grams and molecules. So we have to go to moles, and then from moles to molecules. Okay. Questions? Okay, everybody got it down? You got it, Abdullah? Got it. Okay, so we're just going to do some practice. This one has 2 parts. We're asked for how many moles are in 60 grams of ozone. So ozone is O3. And then we're asked to find molecules. Okay, so you can do this 2 ways. You can do it in 2 parts, or you can just basically put it all together as well. Okay, so it's just like what we did just a few minutes ago. We take 60.0 grams ozone. Okay. How many grams per mole of ozone do we have? Basically, it's 48, right? 16 times 3. Okay, so we get 48. Let's put 0.0. And that's in how many moles? 1. Okay. So if we did the math here to get part A, what would we get? Okay, 60 divided by 48 is 1.25, right? Part B asks for molecules. So we could just go ahead and I would just build on what we already had. I wouldn't even make it a separate step. So to get molecules, we know that in 1 mole of any compound, atom, particle, you name it. I'm writing the wrong thing. Hang on. It's not letting me erase for some reason. So that's O3. All right, in 1 mole, O3, how many molecules do we have? Okay. Well, what am I looking at for up here? I'm looking for 6.022 times 10 to the 23rd molecules ozone. Cancels. Be sure we use our calculator correctly. Okay. Sorry, it's messing up on me again. It's doing that, but anyways, you end up with 7.53 times 10 to the 23rd molecules ozone. If you get a crazy exponent there, you get to the negative or to the 50th or something like that, then it's a calculator issue. So you'll get it worked out. All right. So I want you to do this one. I want you to find the mass in grams of 10.0 times 10 to the 6th SO2 molecules. Okay, so this one's going to be a little bit different, not the steps, it's just the fact that you are given molecules this time and have to go to grams. So you're working really in reverse of the last problem. Okay, just start with what you know, use the correct units, and it's going to be a two-step problem. Okay, we're given molecules. That's where we start. So we know we automatically think of Avogadro's number. So Avogadro's number, the Na there, has to go in the denominator. And so that our molecules can cancel. And it's always out of 1 mole on top. Okay, we have 1 mole SO2 up here in the numerator. So we know we have to have mole SO2 in the denominator here. And it's also 1 because our molar mass of SO2 is based on 1 mole. And on the periodic table, if we add up 1 sulfur atom and 2 oxygens, we should get about 64.07 grams. Okay? So when you do the math, you got to be careful again with the calculators. You should, so you multiply, just to reiterate that, you multiply everything on the top, multiply everything on the denominator, and then divide the denominator into the numerator. Okay? So most calculators, you can do all of it at once, but you should get 1.06 times 10 to the negative 15 grams. Okay, so that's a really small number, right? It's a very small number. Okay, the last thing we're going to talk about today, if I can get it to stay there, is percent composition. Okay, so when you think about a percentage, what do you think of? What's a percentage? You think of 100. Perfect, exactly. It's whatever percentage or whatever part out of 100. So if you get a 95 out of 100, you got 95% correct, right? So you always want to think of a percentage as part over whole times 100. So if you got 95 out of 100, you got a 95% percentage. Okay? It's the same idea when we're looking at the individual atoms in a compound. If you want to know what percentage of that molecule is carbon or what percentage of that molecule is hydrogen. Okay? So we're going back to our propane here. Okay, where we know we've already come up with its molar mass. Okay. If we want to know the percent composition of just the carbon in C3H8, and we can't just say, oh, there's 3 and 8 of hydrogen, so there's more hydrogen. Okay, that's not correct because carbon has a much higher molar mass than does hydrogen. So what we do is we take the mass, the total mass of the carbon, and divide it by the total mass of the compound. So there's your part. You take part of it, the carbon, over whole, which is the whole mass of the compound, times 100. Okay, so if we take 3, we have 3 carbons, times 12.01. Okay, so where did I get that number from? Of carbon. And then what's that number? Yeah, it's the total molar mass of C3H8, right? So that's our whole. So we take part over whole times 100, and we get 81.68%. Okay? 2 ways we could go about finding the hydrogen percent. So if a percentage is out of 100, then what can we do to find the percentage of hydrogen? Yeah, take 100 minus 81.68, and that gives you the rest of the molecule, or the rest of the percentage. Okay, but if we wanted to just show it, we could take 8. We have 8 hydrogens times the molar mass of hydrogen, 1.01, divided by the total mass of the compound, and we get 18.32. Or we could have subtracted and gotten the same thing. The idea here is it's always out of 100. Okay, even when you're in the lab and you have to report a percent yield, it can't be over 100%, right? Okay, there's no way. You can't have more than what you put in. Okay. All right, so last thing, I know we're running all the way to time here. Okay, but work just a couple minutes on this one. So you want to find the percent composition of iron 3 sulfate. That's how we would name it, iron 3 sulfate. Okay. And so you have 2 iron atoms, 3 sulfur, and 12 oxygen. Okay. But the hardest part, maybe not hardest, but you've got to come up with your molar mass, right? So you've got to add up the total mass of the compound. it's, let me see. Yeah, it's an 8. Yeah. Okay, so when it says to do the percent composition, it means for each atom. So you need to do it for iron, sulfur, and oxygen here. So you have to know how to read the formula to see how many atoms you have of each. And then you have to come up with the right molar mass, or then it's all going to be off. Anybody get 399.9 or roughly there for the molar mass? Nobody? You did? Okay, good. Okay, so that's your whole. That's always going to be in the denominator. Now you have 2 times 55.8. That's the atomic mass of iron. 3 times 32.1. Atomic mass of sulfur, and 12 times 16, 16 is the molar mass of oxygen. You divide all of those individually by the 399.9. Okay, hopefully everybody got that, because that's a mistake. If you don't get that right, then everything else will be thrown off. A way to check your answer is to go back. All of your percentages should add up to 100%, right? Because that's what a percentage is. All right, we'll pick up here on Monday, and let me think if you guys, I believe you're off on Monday. Wait, no, I'm trying to think. Did we had lab Monday, right? I'm right getting my weeks running. Yeah, so I think you have Monday off, but I'll send an announcement if I'm wrong. I forgot my calendar again. But have a good weekend. Let me know if you have any questions.